Let us discuss this theorem. So in this theorem, we have two scalar fields f and g. Given that del f and del g exist at A, that means gradient of f and g exist at A. And what we have to prove? Gradient of f upon g, that is also exist at A. This thing we have to prove, as well as we have to prove that del f upon g of A can be calculated in this way also. So we are already familiar with the rule of derivative of u upon v, getting now u into v into derivative of u minus u into derivative of v upon v square. So the same type of rule we have here, okay, but this thing we have to prove. So let us focus on the first part of this theorem. What we have to prove first? We have to prove that del f upon g exists at A. Let us start with the given information which I already written. The given information is del f and del g exist at A, and g of A should be non-zero. Obviously it is non-zero since we take it in denominator, so it should be non-zero, and g also non-zero in some neighborhood of A. So this precaution also they have taken, okay. So this implies, what can we write? So you are familiar with definition of del f and del g. So del f del g exists, that means all partial derivative exist, okay, at point A. So therefore I can write del by f by del by xi of A and del by g by del by xi of A exist for all I running from 1 to n. See, all these partial derivatives are involved in a definition of del f and del g. So they exist. So that's why obviously all partial derivatives of f and g exist at A. So see, these two terms exist. So if you add, if you subtract, if you multiply by any constant, or if you divide by constant, doesn't matter, that term will also exist. So here also I'm going to do the same thing. So this implies, what can we write? G of A del by f by del by xi of A minus f of A del by g by del by xi of A divided by g of A square exist. This is true for all I running from 1 to n. Okay. See what I have done. See, this term exists, right? So I have simply multiplied by one constant g of A. This term exists, so I multiplied by one constant f of A. I did subtraction here, getting, so if these two terms exist, subtraction also, that is also possible, and after at the end we are dividing it by g of A square. So the entire term exists. So this is, it looks like partial derivative of f upon g at A, getting na? So if you apply the formula of u upon v formula of derivative, then we will have the same. So therefore I can write, let us use this space, some space is available here, let us use it. So therefore this implies del by del by xi of f upon g of A exists. This exists for all I running from 1 to n. So that means all, okay, so this is nothing but this one you are getting. So if you apply u upon v formula, we will have this one. So this partial derivative exists, and this is true for all I. That means all partial derivative exist, and partial derivatives are involved in the definition of gradient. So that's why we can write gradient of f upon g of A exist. This gradient also exists. So here we proved it. Yes, del f upon g of A exists. Getting? So after that we have to focus on the second part of this theorem. We have to prove this equality. Okay. Make a screenshot of it. After that we will go further. So let us start with left hand side. Okay. So see, you are familiar with definition of del. So by definition we can write del by del x1 of f by g of A. So that means we find all partial derivatives, getting, so at the end we will have partial derivative of f by g with respect to xi of A, getting. So here I am going to use u upon v formula, denominator into derivative of numerator minus numerator into derivative of denominator upon denominator square. So see, then we will have g of A, right, del by f by del by x1 of A minus f of A del by g by del by x1 of A whole divided by g of A square. Okay, so we can do it for each component. So finally directly I will write for the last. component. So that's why we will have g of a dabba f by dabba xn of a minus f of a dabba g by dabba xn of a divided by g of a square. Okay, see what can we take outside? Each term has g of a square common, so we can take it outside. So therefore 1 upon g of a square in bracket g of a dabba f by dabba x1 of a minus f of a dabba g by dabba x1 of a, getting dot dot dot. So we have taken g of a square common from each term. So finally here also we will have g of a dabba f by dabba xn of a minus f of a dabba g by dabba xn of a, getting. After that, so there is subtraction, so we can express his as a subtraction of two terms of Rn, getting, as well as we can take constants outside, getting. So see that thing I am going to do. So each term has a g of a first, so we can take it common. So this is equal to 1 upon g of a square. See, 2 to 3 terms, 3 steps we are going to do simultaneously. So please focus and try to understand what I am doing. G of a in bracket we will have dabba f by dabba x1 of a and so on, dabba f by dabba xn of a minus f of a. See here I have considered all first terms, right? And now I am considering all second terms. So f of a, see in second term we have a f of a. We can take it outside. F of a in bracket we will have dabba g by dabba x1 of a and so on, dabba g by dabba xn of a. I hope you are getting my point, getting. So see, if you multiply each term by g of a, if you multiply each term by f of a, and if you subtract, we will have the same term again, getting. Are you familiar with this one? This is nothing but del f of a. So this is equal to 1 upon g of a square, okay, square, g of a, this is del f of a minus this f of a, and this is nothing but, you can easily tell me, this is del g of a. That means if you write this thing properly, so finally what will you get? G of a del f of a minus f of a del g of a divided by g of a whole square. That means yes, we got right hand side. We started with left hand side, finally we got right hand side. So in this way we proved this theorem. So make a screenshot of it, then we will stop. Thank you, bye bye.